Okay, so good morning, and this is hopefully going to be a very short video. I don't want it to go on for too long. I don't have a lot of time. I've got finals to prepare for on Sunday for French, so I just wanted to get this out of the way though, especially since I got like maybe 20 minutes, so I think we can get this done in 20 minutes. Backpropagation is very simple. If you understood the forward pass, I think the backpropagation should not be an issue for you as well. So you're going to need these prerequisites though. You're going to need to know to take the derivative. You're going to need to know what a partial derivative is, and you're going to need to know what the chain rule is. I don't want to teach you these things because I realized that's what made the first video very, very long. So, okay, that should not have been a linear algebra video, but in the context of things, I do think it was important. But I won't be doing that here. So, and MIT OpenCourseWare, if you'd like to learn these on your own or any other amazing resources, right? There's so many of them. Or just go query your favorite frontier LLM, right? And have it teach you these things. You don't need advanced calculus. You just need sort of a basic understanding, and you can follow along with what backpropagation is. So let's get up to speed with this example network. We've got x1 and x2, right? This is our feature vector. We've got these weights coming out of the edges of the graph, right? So this is really a graph, right? A directed graph. And we've got z1 and z2. This corresponds to the pre-activation values inside of the hidden layer. We've already been over this, and we've got h1 and h2 now. So this is just going to correspond to after we apply an activation function. Let's say we called ReLU our sigmoid on z1, we're going to get h1, right? Same thing for h2. We've got w5 and w6, so these are the weights for the output layer, and we've got z3 now, that's the pre-activation value for the output layer, and then we've got the output itself. Just got a message, okay, the output itself. So we're not going to call this like h3, we just call it o1 for the first node inside of the output layer, well, the only node in the output layer in this particular case. And so let's look at the matrix itself and run through a forward pass example, and then we'll just get to what backpropagation is. So WL-1, what is this subscript? Well, I just decided to call the last weight matrix WL, and so the weight matrix before that would be WL-1, right? So, okay, and we've already established, right, that the first row of this weight matrix is going to correspond, right, to a particular node inside of that hidden layer. So if you look very carefully, we've got W1 and W3 corresponding to the first node, right? If you look, W1 goes into this first node and W3 also goes into that first node. You can also think of it in terms of columns, right? It's good to have multiple representations of what is going on. And so if you see W1 and W2 in the first column, what does that mean? Look, W1, right, and W2, those are leaving the first input node, right? And sort of spreading out to every single node inside of the hidden layer, okay? And same thing for the second input node as well, right? W3, W4, W3, W4. Okay, hopefully that's clear. And then we go through the forward pass. And so we've seen this WX plus B, and you'll get Z1 and Z2, right? Call your activation function. Well, we'll use sigmoid, not ReLU, just to keep things simple. And ReLU is also very simple, but okay, it's fine. And then you're going to get H1 and H2. We're going to call this A, right? So hopefully you're up to speed there. Now we'll compute for the hidden layer, right? So we'll use the weight matrix for the hidden layer and multiply that by A, because A is now going to be H1 and H2, right? It's going to serve as the input, right, into this. Plus B, we're going to get Z3, call the activation function on Z3, and we're going to get an output here, right? We can also call it YI. And now you have to compute a cost function, and we spoke about this a bit. And we're going to use something called mean squared error. So this is just the formula, right? It's 1 over n, right? Sum of I to n, yi minus yi hat, all squared. And you're going to see this numerically, so don't worry if it looks a bit confusing. It's not. Okay, and so let's use these parameters, right? So we'll say this is going to be the feature vector. This is going to be yi hat. You'll see what this is in a second. WL-1, WL, first bias, second bias. Great. Now let's compute the forward pass with some numbers, and I've already pre-computed these, so you can go ahead and double check or use your own values if you wanted to. It's completely fine. So WL-1 x plus B, and you already know how to do matrix multiplication and addition. You're going to get this for Z1 and Z2, right? And then you call sigmoid, right, on that, and you're going to get H1 and H2. So now you have the the activated neurons, right? And then Z3 now is going to take WL, right, the last weight matrix, times these activated neurons, which is serving as the input now, right, plus the second bias, B1. Well, a 1 because we started counting from 0, but hopefully, if you're a computer science student, that shouldn't be confusing. And you carry out this matrix multiplication, and you get this value here, right? Now you call, and remember, this is going to be Z3, right? So you call sigmoid on Z3 to get the output now, right? And you're going to get this value here. So now once you got your output, you're going to compute the loss. When you do that is using the mean squared error, right? And so what you're going to do is, in this particular case, since we've just got a single output neuron, it's just going to be 1 over 1, right? Let me show you here. Where was it? Right here, right? 1 over n, right? So 1 over 1, well, n in this particular case is how many of the output neurons you have. Okay, where is it? So yeah, so you're gonna get the output value, right? Minus y hat. Remember we said y hat is 1, okay? And you square that value and carry out this computation, and this is what you're gonna get as a loss. Hopefully that's not too difficult to understand. So we can get straight into what backpropagation is. It's a very, very simple idea. So if you understand this, you're good to go. So for all, right, weights and biases in the network, right? This for all weights and biases in the network, compute the partial derivative of the loss with respect to these weights and biases. That's it. If you understood that sentence, you understand backpropagation. And I think an example will sort of help to clarify what I mean. And so let's start with partial derivative of the loss with respect to W5, okay? Now, you cannot compute this directly, right? You should know. So what you're going to have to do is come up here, and this is where you normally use a computation graph, but I don't feel like it's necessary to understanding the backpropagation idea. Look at the chain of events that will happen, right? So let me write this back. So partial derivative of loss with respect to W5, and we'll use some retrograde analysis, right? And we'll say, okay, what happens if we change W5? A small change in W5, and this is where your chain rule will come in, right? So a small change in W5 will affect a small change in Z3, right? A small change in Z3. Okay, I hope you can see why that's happening. And then a small change in Z3, this pre-activation value, will affect a small change in the output, right? Well, in this case, our activation value for the hidden layer. And then now a small change in the output. Remember, what did we do with the output? We computed mean square error on it, right? It's going to affect a small change in the loss. And then we can do some wishy-washy thing that mathematicians hate, right? And you see we get the partial derivative of the loss with respect to W5. And so all you have to do is compute, right? These three intermediate partial derivatives, multiply them, and this is what you're going to get. Very, very simple. So, okay, how are we going to do this? Okay, let's start with partial derivative of the loss with respect to O1, right? And I'm just going to give you what that value is. And again, if you don't know how to do this, please MIT OpenCourseWare or ask your favorite LLM, how do I compute the partial derivative of the mean squared error formula with respect to some output value, right? Okay, so this is just going to be 2 times O1 minus y. And then you just plug in what O1 is, and you plug in what y is for this particular case, and you're going to get negative, oh, I keep using the wrong black, 0.64981, right? So that was very, very straightforward, I hope. And now you just compute the partial derivative of O1 with respect to Z3. Oops. So this guy here, right? And now, so I'm just going to be a bit more explicit with this one. So this is like partial derivative with respect to Z3. And let's just put the function, right, that we're thinking about here. Remember we said it's sigmoid. And again, please, if you have to look up how to take the partial derivative of sigmoid, to do that. And we'll just call this minus Z, but this could be anything really. Well, in this particular case, we're using Z3, so I just made that a bit explicit. Once you compute this partial, you're going to get this value here. and you carry out this. You do your substitution, right? Put in the output value here, put in the output value here, subtract and multiply. This is basic algebra, so I don't have to go into that with you. 0.2. Oh, I don't know why I keep using the wrong color. So weird. 0.2193. Okay, and now this one I'm gonna hold your hand for a little bit, and you're gonna need the partial of z3 with respect to w5. So, oops, partial of z3 with respect to w5. Now, what is z3? How did we get z3? You have to think about this very carefully. Z3 came from, this is the pre-activation, right, of the output layer. So it's a WL, right, times some input value. So let's look and see what that input was, right, for this guy. Where is it? It was A, right? But what was A? A was H1 and H2, right? So let's go put that in here. Times A, which was H1 and H2, right, plus the bias vector. So we can sort of like write this out a bit more explicitly. And so again, let's just remind ourselves what this weight matrix is. It's W5, W6 times, right, H1, H2 plus our bias. And what you're gonna get, right, is H1 W5, right, plus H2 W6 plus the bias. Hopefully you understand how we came about with this from this matrix multiplication. Now we have to take the partial derivative, right, of z3, this entire function, right? This is the function. Like if you want to take this and plug this in place for z3, right, with respect to w5. And so what's going to happen, right, is that this is going to be treated as a constant. Okay, I hope you should know how to take partial derivatives. So this is going to die, this is going to die, and we're going to be left with h, right? This is just 1, and we're left with h. So this is, well, h1, sorry, h1. So this is h1. Like so, okay? And now you just multiply these partial derivatives together, and you're good to go. So what I'm going to do, though, is a little bit of trickery, right? So now you have the partial derivative of the loss with respect to W5, right? You would do the same thing for W6, and you would do the same thing for the bias as well. And you do this for every weight and bias in a network. Okay, and this is the idea of backpropagation. It's not very difficult at all. So what we're going to do, suppose, right, that okay, let me write it back. So partial derivative of the loss with respect to W. Let's do W6, right? So this is just going to be, just give me a second, I'm just writing these out. Very bad handwriting. Times partial derivative of z3 with respect to change in W6. Great. So what we're going to do is we're going to compute the intermediate. Remember, right? We already have this guy. I hope you noticed this. Partial derivative loss with respect to the output. We computed that. Where? Here. Somewhere. Where is it? Here. Didn't we compute that? Hang on a second. I felt like we computed that. Partial derivative loss. Oh, here it is. Yeah, I was like, I'm pretty sure we had computed that. So we already have this partial derivative. So we don't have to compute it again. We can reuse it, right? And then this portion here we can reuse as well. A partial derivative of the output with respect to z3, and we have that value here. So what we're going to do is we're going to carry out this multiplication and use it as an intermediate value. My phone keeps blowing up for some reason. Okay, so I'm just going to silence that thing and put it on mute. Ignore it for now. Okay, so we're going to call this delta tree, right? Don't ask me why. We're just calling it delta tree. This is a variable. So partial derivative loss with respect to O1, and then we're going to do a multiplication, right? Partial derivative of O1 with respect to Z3. Remember, we have these values, so you just plug in these values here that we computed, and you're going to get this, negative 0.649 something 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 something, right? Put in the entire thing. Please do this on your own, right? You have to do this on your own, I think, to understand what's going on. And now, once you have this value, right, you're going to multiply this by the partial derivative of z3 with respect to w6, right? So again, remember we had to come up and define what this z3 value was, but this time it's with respect to w6, right? So what's going to happen though is this is going to go, right? Let me use a different color. This is going to go because it's a constant. This is going to go because it's a constant. Now this is going to turn into 1 and the value is going to be h2, right? So it will be all of this times h2, right? Would give us the partial derivative of the loss with respect to w6. So let's write it out explicitly, very explicitly, so it can't be too difficult to understand. So partial derivative of the loss, and now we'll just with respect to w5. We're getting very close to the end of the video now, so if you understand what's going on here, congratulations, you're good to go. And I would like to encourage you from this point on to do some research on something called computational graphs, okay? And you can use this as a basis to spring yourself forward into some more modern techniques, right? How to vectorize and how it is that autograd works, right? But if you understood this, you understand backpropagation. So, okay. First principles, understanding backpropagation. Okay, and so this, right, is just going to be this delta tree that we computed, right, times, okay, h1, okay, times h1. I hope you understand what's going on here. Times h1, and this is going to give us some value. I don't know what it's going to give us, but it's going to give us something, right? You can do that computation for yourself if you want. And now the partial derivative of the loss with respect to w6, right, is going to be the same delta 3, right, times h2. Well, this one we just explicitly did, okay, and you're going to get some value here as well. And then you compute, so we have the weights, right, for the output layer, and now we just need the bias. So partial derivative of loss with respect to b3, which was the bias. Now this is very interesting because what we're going to get is this delta 3 times the partial derivative of z3 with respect to b3, right? And you're just gonna get this times 1. You're just gonna get 1, and you can take the partial derivative here and convince yourself why we're getting 1. I don't know if I can help you there. Let me see. Where is it? Right. So this is gonna go, this is gonna go, right? And you're gonna be left with 1 here by the b. Okay, if you didn't understand, which you should have understood because partial derivatives is a prerequisite. Okay. And so you can notice, right, that for the bias, right, you're just reusing this delta tree value that we had computed earlier. So that's a very interesting observation that you should make. And okay, so you're almost there. You're almost there. You have these values, right? You're not quite there as yet, though. Not quite there as yet. So let's do an example, not a full example, a conceptual example of what would happen if we wanted to compute the, where's my network? If we wanted to compute now for W1, we have W5, we have W6, and we have B3, right? We need W1, W2, W3, W4, right? And the other bias vector as well, okay? So how are you going to do this? Let's say we wanted it to do for W5, okay? W1, sorry, how would we do that? Well, you start at W1, right? You start with the retrograde analysis I was telling you about. Let me switch to green. And so you're going to say, right, a small change in W1, what's going to happen? A small change in W1 will affect a small change in Z1, right? Affect a small change in Z1. And then a small change in Z1, what does that affect? Affects a small change in H1, right? And now a small change in H1, what does that affect? A small change in Z3, right? And then a small change in Z3, what does that affect? Small change in the output. And now a small change in the output, right? I hope you see where this is going. A small change in the output will affect a small change in the loss. And then these can go. Again, wishy-washy math, but you get the idea. You get the partial derivative of loss with respect to W1. And so you have to compute all of these intermediates now. But you will notice that there are parts of this that you can reuse, and I'm hoping that the pattern will become clear to you, right? How it is that you're reusing this. And then when you go learn about a computation graph, it will become very, very obvious how it is that you actually carry out that, right? So it's not too difficult, I hope. If you have any questions, or if there's something that I did not properly explain, please feel free to let me know. So now, right, once you've computed all of these partial derivatives, you can put it inside of a vector, right? And so this is sort of starting to introduce the idea of a Jacobi. It's not exactly that. It's a gradient vector, essentially, right? And so all of the parameters, 9 parameters in total, you're going to have to collect, right? And so we'll just call this delta theta, like this, of the loss, and we'll flatten it into a vector like this. And so what we're going to do is we're going to put the partial derivative of the loss with respect to W1 here, right? Let me use a different color. And then we'll put the partial oh my god, I keep using the wrong one. Partial derivative of loss with respect to W2 here. I don't know why I put WL. This is supposed to be W1. Okay, and then partial derivative of the loss with respect to W3, right? And then you carry this on W4, W5, W6, and then you do the biases now. So then you do partial derivative of the loss with respect to the first bias, second bias, third bias. And so in total, you're going to have 9 parameters, right? And so this, remember, this is just some numbers, right? These are just numbers that we've computed, right? It's a bunch of numbers. Okay, so that's all the gradient vector is storing. And so the update value, right? And so this is called the vectorized update. It's simply, so theta, right? It's going to be this. Minus n sigma, I don't know what you call it, delta theta times the loss. Well, this is just the particular entry, right? N is what's called the learning rate, right? This is called the learning rate, okay? And so this is gradient descent. Okay, and so how gradient descent works, right? If you imagine we had a parabola like this, okay? And suppose that one of these gradients that we computed, right, was like here. What that's giving you, right, is the direction of steepest ascent, right? But we want to minimize our loss, right? We want to converge towards the lowest point, right, on this graph. And so you're going to take the negative of that, right? Okay, hopefully that's clear to why you're doing that. So that's why you're seeing this negative sign here, right? We want to go in the opposite directions. If we have the direction of steepest ascent, we want to move downwards towards the direction, right, of steepest descent, okay? So hopefully that's clear. Okay, and so you would substitute in your value here, for instance, right? Multiply that by your learning rate, and then subtract off what the actual value is that you have from what you computed. All right, so I hope that was clear. I don't know if I have a very specific example, because I feel like the vectorized update might be a little bit confusing. Let me check my notes. I might have, okay, so I do have a non-vectorized update as well. It's the same idea, really. So what this is, right? So to update the weights, the new weight, I'm gonna type it because unless I get like one of those drawing things, this is gonna be a pain. So the new weight is simply the current weight, this theta value that you're seeing here, right? Plus minus this value here, right? This delta theta thingy, we'll call it delta theta L, right? Times n, right? But this is just a different way to write it, right? So again, let me go it over for you. New weight, we'll call it theta, is equal to current weight, we'll just call this theta 2, right? Not theta 2, not theta 2. Okay, bad language, but hopefully you get the idea, right? So new weight is the current weight, right, times, well, minus in this particular case. If you notice, because this is always negative, this plus sign is going to go negative as well, right? So that's where this minus sign comes from. And we move the n in. So we move the n in, right? And then we put this term inside here, this delta theta L. Okay, delta theta L. Here. Delta theta L. And this is how you're going to update the weights and the biases for the entire network. Okay, so hopefully that's clear. So thanks for watching, and yeah, this still went on longer than I was hoping to, but yeah, have a good one.